And now we'll continue the topic of stability analysis. We have covered some topics in the previous lectures, and that is we defined the stability in the S and time domain both. Then we see the relationship, how the transients are exponentially decaying for the left hand side of the S plane. And then we have seen the classification, absolute and relative stability, and we have seen a method to find the stability, that is the Routh stability criteria. And now we'll see some special cases of Routh stability criteria and another method to find the stability of the system using Hurwitz stability criteria. This is a usual Routh table of the fifth order equation. So we have a fifth order characteristic equation here. We have started with the s raised to the power 5. We have filled this initial two rows by using the coefficients, that is s raised to the power 5, and then the coefficient of s cube is 10 and the coefficient of s is 152. So we have put three variables here, three coefficients here, and then we have filled the second row of s raised to the power 4 first by using the coefficient of s raised to the power 4, that is 1. Then we have put the coefficient of s square, that is 72, and then we have put the coefficient of s raised to the power 0 or constant, that is 240, and then we'll fill this table in the usual manner we have discussed previously. And after completing this Routh table, we have seen here that there are two sign changes in the first column, from +1 to -62, and then from -62 to 70.6. So it means that the system is unstable. So we have seen here a fifth order system. Now we will see some special cases in which sometimes we face some problems to complete the Routh table. The first case is that first element in any one row of the Routh table is 0, but others are not. I think up till now we have seen that we always divide every element while computing the Routh table by the first element of the first column of the Routh table. It means if the first element in any row means in first column, in any row of the first column, if there is a 0, the first element is 0, we cannot complete the Routh table in the usual manner, because by dividing 0 means we will get an infinity answer and we cannot further proceed to complete the Routh table. So if we have a first element in any one row of the Routh table 0, then we use some remedy to complete the Routh table. There are two remedies. The first is, in the characteristic equation Q of S, replace S by 1 upon X, so that the characteristic equation will be a function of X or a function of 1 upon X, that is Q of 1 upon X instead of Q of S. And then complete the Routh table, that is substitute S equal to 1 upon X in the original characteristic equation and then solve for the roots of X with the positive real part. That is, instead of S, then we will solve for the roots of X. This is the first remedy. And the second remedy is another method to complete the Routh table. If we have a 0 in the first column of the Routh table, that we multiply the original polynomial by s plus 1 and then form the Routh table for q dash s or q prime s, that is q of s multiplied by s plus 1. So we say here that q dash s is equal to qs into s plus 1. So we will make a Routh table for q dash s or q prime, and then we complete the Routh table in the usual manner, and we conclude from the Routh table in the similar fashion as we have done previously, that if there is a sign change in the first column, that we will say that the system is stable, and if there is no sign change in the first column, we say that the system is stable, and if there is a sign change in the first column, we say that the system is unstable. Now continue, we'll see some more examples. we'll see examples, and first we discuss the special case 2. If the elements in one row of the route table are all zeros, it means not only the first element in any row of the route table is 0, but all the elements in a row are 0. In this case, we have again do some remedy. That what is the steps? The remedy involves some steps actually. The first, we will make an auxiliary equation, that is a of s equals to 0, by using the coefficients from the row just preceding the row of zeros. That is, if we have a complete row of 0, then what we will do, we'll use the row just preceding the row of 0 and we'll make an auxiliary equation a of s. Then the second step, will take the derivative of the auxiliary equation with respect to s, that is dA upon ds. That is, we take the derivative and we'll equate it equal to 0, and then we'll use the coefficient of dA upon ds, and we will replace the row of zeros by the coefficient of dA upon ds. So it means that we are actually replacing the row of 0, and we are replacing by the coefficients of dA upon ds. And then once we have replaced all the zeros, then we can continue the route table in the usual manner. So if we have found that the elements in one row of the route table are all 0, yani ki it means that all the terms are actually in one row are actually 0, then we say that we'll use remedy 2. We'll make an auxiliary equation, we'll take the derivative, and then we'll replace the row of 0, and we continue the route table in the usual manner. And we conclude also in the usual manner that if there is a sign change in the first column, that the system is unstable, and if there is no sign change in the first column, we say that the system will be stable. Now we'll see an example. Find the stability of the control system having the characteristic equation s raised to the power 4 plus s cube plus 2s square plus 2s plus 5 equals to 0. So again we have started with the highest power of s raised to the power 4, and then s cube, s square, s1, s0 in the extreme left column. We have filled the first two rows by using the coefficients of the characteristic equation. So if we have filled the s raised to the power row, s raised to the power 4 row by the coefficients, alternate coefficient s raised to the power 4 is 1, the coefficient of s square is 2, and then 5. And then we filled the second row by using the coefficient of s cube, that is 1. Then the alternate coefficient of s raised to the power 1 is 2. So we have filled. Then we continue the table. We multiply 1 multiplied by 2 minus 2 multiplied by 1, that is 2 minus 2 is 0. 0 upon 1 is 0. Then we'll calculate this term. 1 multiplied by 5 is 5 minus 0 multiplied by 1 is 0. That is 5 minus 0 divided by 1. This is actually equal to 5. It means this is actually the special case 1, in which we have said that if the first element in any one row of the route table is 0. So here this first term is actually 0. So it means this is special case 1, and we have to apply some remedy so that we can complete our route table and we can conclude that whether our system is stable or unstable. So we have seen two remedies. For the first case, we will apply this is special case 1. So in the first remedy, we have replaced q of s by q of x. So we have replaced s by 1 upon x. So s raised to the power 4 will become 1 upon x raised to the power 4. Then s cube is 1 upon x cube. Then 2s square is 2 upon x square. 2s is 2 upon x plus 5 upon 1. S raised to the power 0 is actually 1, equals to 0. We have taken the LCM here. The highest is x raised to the power 4, and then when we simplify this, it will become 5x raised to the power 4 plus 2x cube plus 2x square plus 2x plus 1 equals to 0. So we are now completing the route table. We have started with the highest power of x, that is x raised to the power 4. Then we continue x cube, x square, x raised to the power 1, and x raised to the power 0. We filled the first two rows by using the coefficients of the route table. The coefficient of x raised to the power 4 is 5, and then the alternate coefficient 5, 2, 1. And in the second row, 5, 2, and 1, and in the second row the coefficient of x cube is 2, and then we have a coefficient 1 here, so we have put here 1, and there is no other term, so we have put a 0 here. So we have calculated x square row. 2 multiplied by 2, 4 minus 5 upon 2, that is minus 1 upon 2. 2 multiplied by 1 minus 0 multiplied by 5 upon 2, that is equals to 1. And just to simplify, we have multiplied this by 2, so it will become minus 1 and 2. We can skip this step if we want, otherwise we can simplify this too. So now we will use this x cube row and this x square row. We will not use this x2 row. So we'll ignore this row and we'll use x3 and x2, sorry, x square, that second and fourth row, and then we'll complete x1 5 multiplied by minus 1 multiplied by 1, minus 2 multiplied by 2 4, that is minus 1, minus 4 is minus 5, divide by minus 1, it will become 5, and then we'll have 2 here, 2 multiplied by 5 minus 0 upon 5 is 2. So we have completed this table by using first remedy, and we have seen that there is a sign change in the first column from plus 2 to minus 1, that is one sign change, and then from minus 1 to 5 again there is a sign change. There are two sign changes in the first column, therefore the system is unstable. We can also use the second remedy when we fail to complete the route table and we notice that this is the case 1. We can also use the second remedy. The second method is that we multiply our characteristic equation by s plus 1. What is s plus 1? Is actually a factor with a pole at minus 1. So obviously it is stable. It does not change the stability of the system. So here we have q of s equal to s raised to the power 4 plus s cube plus 2s square plus 2s plus 5 equals to 0, and when we multiply by it by s plus 1, and the new characteristic equation will be q prime s, and when we simplify this multiplication, the new characteristic equation will become s raised to the power 5 plus 2s raised to the power 4 plus 3s cube plus 4s square plus 7s plus 5 equals to 0. So this time we will make route table for this characteristic equation, which is actually 1 degree higher. So we'll start with s raised to the power 5, and we'll continue the first column. First left column is s raised to the power 5, then s raised to the power 4, then s cube, then s square, then s raised to the power 1, then s raised to the power 0. So again we continue. We fill the first two rows by using the coefficient. The coefficient of s raised to the power 5 is 1, s cube is 3, s coefficient of s is 7. So we have written here in the first row 1, 3, 7. The coefficient of s raised to the power 4 is 2. The coefficient of s square is 4, and the coefficient of s raised to the power 0 or constant is 5. So we have put here in the second row 2, 4 and 5. Now we fill the third row by the method we have studied. So 2 multiplied by 3 is 6, 6 minus 4 is 2, 2 multiplied by 3 minus 4 multiplied by 1, that is 6 minus 4, that is 2, 2 upon 2 divided by this 2, that is equal to 1. So we have written here 1, then 2 multiplied by 7 minus 5 multiplied by 1 divided by 2. The 2 multiplied by 7 is actually 14. 14 minus 5 is 9. This is 9 upon 2. So again, just for simplification, we multiply this by 2, and our new s cube row will become 2 and 9. Now we will use this s raised to the power 4 and this s cube row, and we will not consider this one. We will ignore this highlighted row. Now we continue the table in the usual manner. We have multiplied 2 multiplied by 4 minus 9 multiplied by 2 upon 2 is minus 5, and then 2 multiplied by 5 minus 2 multiplied by 0 upon 2 is equals to 5. Then minus 5 multiplied by 9 minus 5 multiplied by 2 upon minus 5 is 11, and the last value here is 5. So again we can see easily here that there are two sign changes in the first column. From in the s cube row plus 2, and in the s square row it is minus 5, that is from plus 2 to minus 5, and then again minus 5 to plus 11 in the s raised to the power 1 row. It means that again we have obtained the same result by using remedy 1 and remedy 2. Both results are same. In both route table, the system is obtained as unstable. We have found that the system is unstable with two sign changes in the first column. It means that there are two roots in the right half of the S plane. So there are two roots with the positive real parts and the system is unstable. So by applying both of the remedies, we have obtained the same result, that the system is unstable with two sign changes in the first column. Now we'll see some other example. This is actually example number 6. Find the stability of the control system having the characteristic equation s raised to the power 5 plus 4s raised to the power 4 plus 8s cubed plus 8s square plus 7s plus 4 equals to 0. So first we write the left hand extreme left column, starting with the highest power of s raised to the power 5, then the decreasing power of s raised to the power 4, s cube again, and then s square, s raised to the power 1, s raised to the power 0. So s raised to the power 5 is 1. So s cube, in the s cube row we have 660, and in the s square row we have 440, and then we go to s raised to the power 1 row. S raised to the power 1 row is actually 4 into 6 minus 4, 6 into 4, that is 24, minus 24 upon 4 is 0. Then for this we have 4 into 0, 0, minus 6 into 0, 0, minus 0 is 0, upon 4 is 0. And it means that this is the case 2. The s raised to the power 1 row is all zeros. So we have a complete row of 0, and this is actually special case 2, that if we have all the elements in any row of the route table are 0, then we say that this is special case 2, and we see the remedies for it. We have to follow some steps, and then we'll continue the route table in the usual manner. This is actually just a glimpse back to the remedy, and we have to follow these steps. We have to make the auxiliary equation, and then we have to write, we have to take the derivative of this, and then we have replace the row of zeros by the coefficients of d upon ds. So here actually the s square row is actually zeros. So we have made the auxiliary equation as 4s square plus 4 by using the coefficients of the rows just preceding the row of 0. And then we have made the derivative. We have taken the derivative, that is d upon ds is equals to 8s. When we have d upon ds equal to 8s, we replace the row of 0, that is the row of s raised to the power 1, by using the coefficients of d upon ds, that is 8s equals to 0. So the coefficient of s is 8, and there is no other alternate coefficient, so we have put a 0 here. And we complete the route table in the usual manner, that is 8 multiplied by 432 minus 0 upon 8, that is equals to 4. So now it is very clear from here that there is no sign change in the first column, so it means that the system is stable. So we conclude here that the system is stable. This is another example. Find the stability of the control system having the characteristic equation s raised to the power 5 plus 2s raised to the power 4 plus 24s cubed plus 48s square minus 25s minus 50 equals to 0. So we have started with s raised to the power 5, then s raised to the power 4, then s cubed, then s square, s raised to the power 1, s raised to the power 0. The coefficient of s raised to the power 5 is 1, the coefficient of s cube is 24, and the coefficient of s is minus 25. So we have written in the first row 1, 25 and minus 25, the alternate coefficients. In the second row, the coefficient of s raised to the power 4 is 2, so we have put as 2 here. Coefficient of s square is 48, so we have written here 48, and the alternate coefficient of is minus 50. So we have put a minus 50 here. Then we continue the route table. 2 multiplied by 24 is 48, minus 48 multiplied by 1 is 48. Divide by 2, that is 48 minus 48 upon 2 is 0. So this is a 0 in the first element of the row, but To check that whether it is case 1 or case 2, we complete this row. So we have 2 multiplied by minus 25, that is minus 50. 2 multiplied by minus 25 is minus 50. Minus 50 multiplied by 1. So minus 50 multiplied by 1 is minus 50, and because there is a negative sign, we have to subtract the product of minus 50 and 1. So minus 25 plus 25 upon 2. Sorry, minus 50 plus 50 upon 2 is 0. So again we have a 0 in the second term here. Now there is no column next to this, so it means there is a 0 here. So we have a 0 0 0, or a row that has all the elements equal to 0. So we have concluded here that this is case 2, and for case 2 obviously we have to apply some remedies in the steps. So we'll continue the route table by applying the steps of the remedies, and then we see that whether the system is stable or unstable. Right now we cannot say that whether this system is stable or unstable. Now we'll apply some remedies. All the steps involved in the remedy of case 2, when we have all the elements in any row of the route table are all 0. So the first step is to form the auxiliary equation A of S by using the coefficients from the row just preceding the row of zeros. So here actually the S cube row is 0. All the elements in the S cube row are 0. So we have used the coefficient of S raised to the power 4 to make the auxiliary equation. So the first coefficient is actually the coefficient of S raised to the power 4. So we have written here 2s raised to the power 4 plus 48s square. We have written 48s square because these are actually the alternate coefficients. So 24s raised to the power 4 plus 48s square minus 50s raised to the power 0, or we simply write it as 50. So auxiliary equation will become 24s raised to the power 4 plus 48s square minus 50 equals to 0. Then we'll take the derivative of this auxiliary equation. So dA upon ds will become 8s cube plus 96s equals to 0. 50 is constant, so its derivative will be 0. So dA upon ds will be 8s cube plus 96s equals to 0. And then we will replace the row of 0, that is the row of s cube, by the coefficient of the dA upon ds. So we will continue the route table in the usual manner by replacing the row of 0 by the coefficient of dA upon ds in s cube row. So we have replaced s cube row by using the coefficients of dA upon ds. We have written 8 and 96 0. And then we have completed the route table in the usual manner. Here 8 multiplied by 48, 8 multiplied by 48 minus 96 multiplied by 2 upon 8 is equals to 24. 8 multiplied by minus 50 divided by 2 multiplied by 0 upon 8 is minus 50. There is no next column, so we have put a 0 here. Now 24 multiplied by 96 minus 50 multiplied by 8, so it will again actually become plus. Divide by 24 is 11.27. Here we have 0 0, so there is a 0 here, and 11.27 multiplied by minus 50 divided by 11.27, it means we have minus 50 here in the last column. So this time we can say that there is one sign change in the first column. So there is a sign change in the first column, so we say that the system is unstable with one sign change. With one sign change means that there is one root that lies in the right half of the S-plane or with positive real part. So after applying remedy for the case 2, we have completed the route table, which we cannot complete without applying the remedy, and we have concluded that the system is unstable with one sign change in the first column. Now we see that how we can stabilize control gain, or we can change some parameter value in a particular range such that the system will remain stable. So here's another problem. Find the range of k so that the system having the characteristic equation s cube plus 3s square plus 3s plus 1 plus k equal to 0 will remain stable. Here the method is same. We'll make the route table in the same manner we have made previously, but here instead of all the values as constants, we have some variable value like k here, and we have to find the range of k for a stable system. There is a range of k for the stable system. We have to find that range. So we'll make the route table in the usual manner. The first is the highest power of s is s cube. So we have s cube, then the next row is s square, s raised to the power 1, and then s raised to the power 0. The first coefficient of s cube is 1, the coefficient of s is 3, and there is no other alternate coefficient. In the second row, the coefficient of s square is 3, and the alternate coefficient this time is 1 plus k. So we have written 1 plus k here. We have completed the route table in the usual manner, that there is 3 multiplied by 3 is 9, minus 1 multiplied by 1 plus k is minus 1 minus k, divided by always the first element of the row just preceding the row where we are calculating, that is we will divide by 3. So it will become 9 minus 1 minus k upon 3, that is equals to 8 minus k upon 3, and as there are two zeros over here, so we'll have a 0 here. 3 multiplied by 0 minus 0 multiplied by 1 upon 3 is equals to 0, and there is no column here, so here we have a 0. Now in the s raised to the power 0 row, 8 minus k upon 3 multiplied by 1 plus k minus 3 multiplied by 0 is actually 0, and the whole term is divided by 8 minus k upon 3. So simply 8 minus k upon 3 multiplied by 1 plus k upon 8 minus k upon 3. So 8 minus k upon 3 will be cancelled in the denominator and numerator, and the answer will be 1 plus k equals 1 plus k. So this time we can see easily that in the first column of the coefficients, we have 1 with a positive sign, obviously 3 with a positive sign. 8 minus k upon 3 is actually a variable with a variable k, and 1 plus k. So in order to ensure that the system will be stable, this term should be positive and this term should be positive. That is 8 minus k upon 3 should be greater than 0, and 1 plus k should be greater than 0, so that all the terms here in this column are positive and the system will be stable. So we have written here from the route table that 8 minus k upon 3 is greater than 0, or 1 plus k upon 3 1 plus k is greater than 0. So when we simplify this, we'll get that 8 minus k upon 3 is greater than 0. So 8 minus k is greater than 0, or alternatively we can say that k should be less than 8. Or when we say that this term should be positive, 1 plus k is greater than 0, we can say that k should be greater than minus 1. So by combining these two equations, we have a range that k should be greater than minus 1 and should be less than 8 for the system to be stable. We can also prove it by using some different values of k in the characteristic equation, that system will remain stable for the range of k, which is minus 1 to 8. Also please note that if we have a 1 plus k term here, it will be of no use to find the range of k. We are just interested in the values in this column, in the first column of the coefficients. So these two should be positive, and by combining these two we have a range that k should be between minus 1 and 8 for the system to be stable. The characteristic equation of the system is s raised to the power 4 plus 6s cube plus 11s square plus 6s plus k equals to 0. What restriction must be placed upon the parameter k in order to ensure that the system is stable? Again, we have made the route table. The coefficient of s raised to the power 4 is 1, the coefficient of s square is 11, the coefficient next of s raised to the power 0 is k. Then s cube is 6, coefficient of s cube is 6, coefficient of s is 6, and then we have a 0. There is no other alternate term here. Then we fill the next row. 6 multiplied by 11 minus 6 upon 6 is 10. 6 multiplied by k minus 1 multiplied by 0 upon 6 is k. 10 multiplied by 6 is 60 minus 6k upon 10. Then 10 multiplied by 0 minus 6 multiplied by 0 upon 10 is 0. Again we have a 0 here. Now 60 minus 6k multiplied by k minus 0 multiplied by 10 is actually 0. So 60 minus 6k upon 10 multiplied by k upon 60 minus 6k upon 10. So this term will be cancelled and we will simply have a k here. So again the condition is that this 60 minus 6k upon 10 should be greater than 0 and this k should be greater than 0. We can simply write it as either 60 minus 6k upon 10 is 0, greater than 0, or k is greater than 0. When we simplify this, 60 minus 6k is greater than 0, k should be less than 10, and by combining this two, we say that the k should be greater than 0 and less than 10. So we have a range here that k should be between 0 and 10, and the system will be stable for this range. Now this is another example. Find the range of k for a control system whose characteristic equation is s cube plus 15s square plus 50s plus 250k equals to 0. Also find the pure imaginary roots. So for the range of k, we'll make the simple route table starting with the s cube, then s square, s raised to the power 1 and s raised to the power 0 here in the first column, and then we have filled the first two rows by using the coefficients, that is 1 and 50 alternate coefficient, and in the second row the coefficient of s square is 15 and the alternate is 250k. Then we will complete the route table. 15 multiplied by 50 minus 250k upon 15. We have first simplified this s square row by dividing it by 5, and then we have completed the route table. So we again we use these two rows to calculate s raised to the power 1 row. So this is 3 multiplied by 50 is 150 minus 50k upon 3. This is 0, 50k and 0. Obviously when we multiply these two terms, minus 0 divided by this term, we'll get 50k here. So first we have to find the range of k. So to find the range of k from s raised to the power 1 row, we know that 150 minus 50k upon 3 should be greater than 0 or positive, as all these terms are positive, and 50k should also be greater than 0. So here 150 minus 50k upon 3 should be greater than 0, and when we simplify this, we'll get that k should be less than 3. And from s raised to the power 0, k should be greater than 0, as 50k should be greater than 0, or it is equivalently to it is k is greater than 0. So when we combine these two ranges, we get a range that is k is between 0 and 3. The range of k is 0 and between 0 and 3. Now to find the pure imaginary roots, we find equation or auxiliary equation from s square row. The s square row has actually two pure imaginary roots. Always the even powers of s give us the imaginary roots. So we make equation s square, the coefficient of s square is 3. So 3s square plus 50k equals to 0. And for the marginally stable, we put the higher range because we have a marginally stable systems when we have pure imaginary roots on the j omega axis. We have discussed in detail while we were defining the stability. So 3s square plus 50 into 3 equals to 0. So 3s square plus 150 equals to 0, or alternatively we can write s square equals to minus 50, and the two pure imaginary roots are s equals to plus minus j 7.07, that is the under root 50. So we have used this route table here to find the range of k, and we have used to find the pure imaginary roots. For what next example is for what value of k does the polynomial s raised to the power 4 plus 8s cube plus 24s square plus 32s plus k have roots with 0 real parts, and what are these roots? So roots with 0 real parts are actually Again the imaginary roots. So we have completed the route table in the usual manner. S raised to the power 4 s cube s square, s raised to the power s raised to the power 0, and then we have filled the first two rows by the coefficients 1, 24k, 8, 32, 0, and then 8 multiplied by 24 minus 32 upon 8 is 20. 8 multiplied by k minus 0 upon 8 is k. 20 multiplied by 32 minus 8k upon 20. Here 640 minus 8k upon 20, and then we have a 0 because we have two zeros here. And 640 minus 8k multiplied by upon 20 multiplied by k upon 640 minus 8k upon 20 will be equals to k. So we have completed the route table. Now we'll find the value of imaginary roots. So again from s raised to the power 1 row, 640 minus 8k, this time we have put it equal to 0 because actually we are going to find the pure imaginary roots for marginally stable system. Otherwise for stable systems we have written previously that 640 minus 8k upon 20 is greater than 0. So we have written here at 640 minus 8k upon 20 equals to 0, and by solving this we get that k will be equals to 80, and by putting the value of k equals to 80 in the row we have made using the coefficient of s square. So just 20 s square plus k equals to 0, and we have put the value of k equals to 80. So 20 s square plus 80 equals to 0, and s square equals to minus 4 and s equals to plus minus j2. That are the pure imaginary roots for marginally stable system. Next is another method to find the stability, that is Hurwitz stability criteria. We use the same characteristic equation, q of s equals to a n s raised to the power n plus a n minus 1 s raised to the power n minus 1 plus a n minus 2 s raised to the power n minus 2, and so on up to a naught s raised to the power 0 equals to 0. This time we have made determinants in order of the highest power of s, that is n. So we have made a determinant here is del n. We use the coefficients. The coefficient of s raised to the power n is an. The coefficient of an minus 1 is the coefficient of s raised to the power n minus 1. So here we have first write the coefficient of s raised to the power n minus 1, that is an minus 1. Then we have used again the alternate coefficients, and it will goes up to a naught if n is odd automatically, and it will reach up to a1 if n is even. So when we complete this determinant, we will see that it will complete at a naught or a1 depending upon the power of s, and then we'll complete the route table by adding zeros to make it order n. Then in the second row we use the coefficient of s raised to the power n, then again the alternate coefficient an minus 2, and so on. Again it will end up to a1 or a naught, and will complete by adding 0 the order n. Again the first two rows are actually solved, are actually filled completely by the coefficients, and then we have just put these things here in the third and fourth column. So just we have put a 0 0 here, and then we have copied this term. This is the determinant actually, an minus 1, an minus 3, an, the whole we have just copied here. Similarly we will just copy the next in the next rows by adding zeros in the next rows, and we complete, and automatically it will complete at a naught. So we'll see in the examples how we'll complete this del n, and after completing the del n we have to find del n minus 1, del n minus 2 up to del 1, and del 1 is of order 1. So the first term is actually making del 1, the second is del 2, 2 rows 2 column. Similarly if we take 3 rows and 3 column, it will make del 3, and so on. So we have made the first determinant del 1, this is an minus 1. The second determinant del 2 is actually 2 by 2, order of 2 by 2, an minus 1, an minus 3, an minus 2, and we can simplify it by an minus 1 multiplied by an minus 2 first, then the subtract the product of an and an minus 3. So we'll expand it like this, like we expand the determinants. The del 3 is order 3, an minus 1, an minus 3, an minus 5, an minus 2, an minus 4 in the second row, and the 0, an minus 1, an minus 3 in the next row. And we'll continue it up to del n minus 1. We have already calculated del n, and then we have made these determinants del 1, del 2, del 3 up to del n minus 1 using del n. We can expand this del 3. I hope all of you have remembered how we expand this. It is easier if we expand it by column 1, or otherwise we can expand either by column 1, column 2, column 3, or row 1, row 2, row 3. I hope all of you have remembered, you have done in the mathematics. So I think it's easier if we expand it using column 1, otherwise you can expand it anyway. And the Hurwitz stability criteria is that all the roots of the characteristic equation have a negative real parts, that is the system is stable if and only if del i's are greater than 0. So we have to calculate all del i's. We have to calculate all del i's to check the stability, and then we'll see if all del i's are greater than 0 or positive. Then we say that the system is stable, that all the roots lie in the left half of the S-plane. This is the third order equation, a3s cube plus a2s square plus a1s 1 plus a0 s naught equals to 0. So here we have made the determinant del n as del 3 because the third order equation. So we have used the coefficient of s square first, that is the coefficient of s to the power n minus 1. So s to the power n minus 1 is here s square. So coefficient of s square is a2. Then the alternate coefficient is a0, 0. Then coefficient of s to the power n, which is here s cube. So coefficient of s cube is a3. Then alternate a1 and then 0. And then we copy this a2, a0. Then we copy this a2, a0 here. Copy this a2, a0 here. So when we copy this, it automatically ends at a0 as we have discussed previously. Then we expand it a2, and we have made the determinant a1, a0 cofactors minus a0 square a3 because we have expanded using row 1. So a2, it will become a3, a0 and multiply by that. You can obviously do it yourself. Then del 2 here is a2, a0 and a3, a1 like this. Sorry, this is a2 and this is del 2 and this is del 1 of order 1. So this is del 1. So we can easily see here del 1, del 2, del 3, and we calculate the value, and the system will be stable if these three values are greater than 0. Now we'll see an example. This is q of s equals to s to the power 4 plus 3s cube plus 6s square plus 9s plus 12 equals to 0. So we used these coefficients for del 4. So the first is the coefficient of s cube is 3, then 9, then we have put 0, 0 here just to make it out of order 4 by 4. Then coefficient of s to the power 4 is 1, 6, and then 12. Again we have put a 0 here. Then we simply copy this 3916 here. We have simply moved it from here to here. This is how we complete it. And the next we'll put 12090. So obviously because of the order 4 by 4 we have only 12 here. So we'll put this here. If order is greater than 4, then we'll put whole this 12090 here, and so on. We'll complete it. So this time we have del 4 3900 1612 0390 01612, and then we calculate. Obviously it is quite easy to expand it either row 1 through row 1 or column 1 or column 3. If you expand it by this third column, you will see that it is very easier because we have 3 zeros here. So the signs are 3 plus 3. When we expand using cofactors, we use the sign plus minus plus minus. So here the minus plus minus plus. So this is actually plus 12. When we expand, this will become plus 12, and when we use to expand by this row, we'll not consider this row, we'll cancel, if you have remembered, and we cancel this row also. So the determinant of order 3 by 3, 390, 1612, 039. When we calculate this del 3, we'll get that del 3 is minus 27. So to expand this del 4, we multiply 12 by minus 27, which is actually a negative number obviously, and del 3 is negative. So we see here that these two terms are negative. So obviously the system is unstable, because this the condition is that all del i's should be greater than 0. So there is no need to calculate del 1, del 2. We can calculate, but del 1 is 3, del 2 is 9. But we have already concluded that because del 3 and del 4 are greater than 0, therefore the system is unstable. So we have studied the stability in detail. I hope all of you have understand the concept of stability in the control system.